Everything you see began from a single point. The grandest mystery of all is the origin of the cosmos itself. Today we are tackling 30 of the biggest, most mind-bending questions about the formation of the universe. This is a journey from the very first unimaginable instant to the fate of the last star. You will walk away with a clear map of our cosmic story, from nothing to everything. We will ask what sparked existence and what shape the empty future holds. What is the one question about the beginning of everything you most want answered? The very first question is perhaps the most frustrating of all. What was before the Big Bang? Our entire story of the cosmos begins with that moment of explosive expansion, but it feels incomplete. Surely something must have come before. This is where our intuition, built in a world of cause and effect, runs headlong into a cosmic wall. The Big Bang is not just an event in space and time, it is the beginning of space and time. Asking what happened before it is like asking what lies north of the North Pole. The concept of before loses all meaning when time itself is created in that instant. Our most trusted laws of physics, Einstein's relativity, break down completely at that initial point of infinite density, the singularity. It is a boundary beyond which our science as we know it cannot see. Yet the human mind refuses to accept a blank page, so scientists propose speculative, breathtaking ideas. Perhaps our universe is part of an endless cycle, a cosmic heartbeat where a big bang follows a big crunch over and over for eternity. Or maybe our universe is just one bubble in a vast, frothing multiverse, eternally bubbling up from a deeper reality. Some theories suggest a state of quantum foam, a seething, chaotic sea of potential where universes pop into existence spontaneously. While we lack proof, these are not wild guesses. They are mathematical explorations of what could lie beyond the edge of our understanding. They remind us that the first moment may not be the absolute beginning, but simply the start of our chapter in a much grander and stranger story. That blank page before time taunts us with a deeper puzzle. If the Big Bang was the beginning, what was the spark that lit the fuse? This is the ancient riddle of the first cause, and modern cosmology approaches it with a radical idea. Perhaps nothing, truly nothing, is unstable. Think of the void not as an empty stage but as a restless sea. According to quantum physics, even perfect emptiness seethes with potential. Particles and their opposites, matter and antimatter, can flicker into existence for the briefest moment before vanishing again. This is a quantum fluctuation, a tiny tremor in the fabric of reality itself. Now stretch that idea to its ultimate limit. Could our entire universe be the result of one unimaginably vast quantum fluctuation in a primordial nothingness? A single, definitive pop of something from absolute nothing. Some theories go even further. In the realm of string theory, our universe might exist on a vast, rippling membrane or brain floating in a higher dimensional space. The Big Bang could have been triggered by a cataclysmic collision between our brain and another, a cosmic crash that poured immense energy into our newborn cosmos. Another profound idea comes from quantum cosmology called tunneling from nothing. It suggests the universe did not explode from a point, but rather quantum mechanically tunneled into existence. Picture a hill with one side representing nothingness and the other representing a tiny, expanding universe. According to quantum rules, the universe could have appeared on the other side of that hill without ever having to climb over it, appearing spontaneously because the probability, while incredibly small, was not zero. We are left at a breathtaking frontier. These are not just scientific models, they are modern answers to a question that has lived in philosophy for millennia. Why is there something rather than nothing? Today, that question sits precisely where our most advanced physics meets its limits, in that fleeting instant where all the rules we know were written. The universe's first second was a lifetime. Within that fleeting heartbeat, reality transformed more radically than it has in all the billions of years since. To understand it, we must slice that second into epochs, each a distinct chapter of cosmic evolution. The story begins at time zero, the moment of the Big Bang itself. This is the Planck epoch, a duration so short it defies human comprehension, lasting from time zero to about 10 to the power of negative 43 seconds. In this era, the universe was smaller than a single subatomic particle, yet contained all the mass and energy of everything we see today. Density and temperature were literally infinite, and the four fundamental forces we know, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into a single, unified superforce. Our current laws of physics simply cannot describe what happened here. It is the ultimate veil. As the universe expanded and cooled past that unimaginable threshold, it entered the grand unification epoch. Here, gravity split away, becoming its own distinct force, but the other three, electromagnetism and the nuclear forces, remained unified. The cosmos was a seething, hot soup of the most fundamental particles like quarks and leptons, constantly popping in and out of existence in a frenzied dance of energy. This state held for only a minuscule fraction of a second, but it set the stage for the next and perhaps most dramatic act, cosmic inflation. Then, around 10 to the power of negative 36 seconds, something extraordinary happened. A phase transition, like water freezing into ice, occurred as the strong nuclear force separated from the electroweak force. This event released a colossal amount of latent energy, causing the fabric of space itself to expand at a rate far beyond the speed of light. This is the inflationary epoch. For a mere sliver of time, until about 10 to the power of negative 32 seconds, the universe doubled in size over and over again, perhaps 100 times or more. In that instant, a region smaller than a proton was stretched to a size larger than our entire observable universe today. Why is this bizarre idea so crucial to our modern model? It solves two profound puzzles. First, the horizon problem. Look at opposite sides of the night sky. They are so far apart that light has not had time to travel between them since the Big Bang, yet they have the exact same temperature and properties. How can two regions that have never been in contact be so perfectly uniform? Inflation answers this by stating they were in contact, crammed into that tiny, hot region before inflation blew them apart. Second, the flatness problem. Our universe's geometry appears incredibly flat, a precise balance between expansion and gravitational pull. Inflation acts like blowing up a balloon to cosmic scales, stretching any initial curvature so smooth it appears flat to us. Without this explosive growth spurt, our universe would likely look very different, perhaps too curved and chaotic for galaxies, stars, or us to ever form. So, in less than a second, the universe went from a unified, unknowable singularity to a vast, smooth, and flat expanse, setting a perfect table for everything that was to come. Inflation stretched the infant universe so rapidly it left behind a permanent fossil, a whisper of its immense power. That whisper is the cosmic microwave background, a nearly uniform glow of radiation that fills every direction of the sky. It is the cooled and stretched afterglow of the universe's hot, dense youth, a snapshot from when it was just 380,000 years old. Its incredible uniformity, its sameness in temperature to within 1 part in 100,000, is our first and strongest clue that inflation occurred. Without that explosive smoothing, different regions of the sky would show wildly different temperatures, having never had time to mix and balance. The second key piece of evidence is the geometry of space itself. Observations tell us the universe is flat or very nearly so. This is a precise and unlikely condition, like balancing a pencil perfectly on its tip. Inflation naturally produces this flatness. Think of a tiny, wrinkled raisin. As you blow it into a giant balloon, its surface becomes smooth and flat from your local perspective. Inflation did exactly that to the fabric of the cosmos. But the most compelling evidence is not just in the smoothness, but in the tiny imperfections within it. The cosmic microwave background is not perfectly uniform. It contains minute variations in temperature, tiny ripples of slightly denser and slightly less dense regions. These are the cosmic seeds, the gravitational fingerprints of the quantum fluctuations that were stretched to astronomical sizes during inflation. These microscopic jitters in the primordial energy field became the blueprint for the entire cosmic web, the gravitational anchors around which galaxies and clusters would eventually form. This precise pattern of fluctuations predicted by inflation theory matches the observations with stunning accuracy. It is a direct link between the quantum world of the unimaginably small and the grand structure of the cosmos. The final, elusive proof scientists seek are primordial gravitational waves. Inflation, a period of such violent stretching, should have sent powerful ripples through the very fabric of spacetime itself. These waves would have left a distinct, swirly pattern in the polarization of the cosmic microwave background light. Finding this signature would be the smoking gun, the definitive confirmation of inflation's most dramatic moments. While we have strong indirect evidence, the direct detection of these ancient ripples remains one of the great quests in cosmology, a hunt for the first tremors of creation. That ancient light from the end of inflation holds the answer to our next great question. What is the cosmic microwave background, and why do we call it the baby picture of the universe? To find it, we must travel forward in time from those first frantic moments. For nearly 400,000 years after the Big Bang, the universe remained a searing, opaque fog. It was a plasma, a soup of free protons, electrons, and light particles called photons. Photons could not travel in a straight line. They were constantly scattered, bounced, and absorbed by the dense sea of charged particles. Light was trapped. Then, as expansion continued its relentless work, the cosmos cooled to a critical threshold about 3,000 degrees Celsius. At this temperature, something monumental happened. Protons and electrons finally had enough energy to combine and form the first neutral hydrogen atoms. This event is called recombination. In an instant, the fog cleared. With no more free electrons to scatter them, the photons were suddenly set free. They began streaming across the universe in every direction, and space became transparent for the very first time. That first flash of liberated light is what we detect today as the cosmic microwave background. It is the afterglow of that hot, dense state, stretched and cooled by 14 billion years of cosmic expansion. Its discovery was one of the great accidental triumphs of science. In the mid-1960s, two radio astronomers, Penzias and Wilson, were working with a giant horn antenna in New Jersey. They were plagued by a persistent, annoying hiss of microwave noise that came from every direction in the sky. They scrubbed the antenna, checked for pigeon droppings, and eliminated every possible source of interference, but the hiss remained. Unbeknownst to them, a team of physicists at Princeton, led by Robert Dicke, had just predicted the existence of this very signal, a relic glow from the early universe. When the groups connected, the penny dropped. Penzias and Wilson had not found a technical flaw. They had stumbled upon the oldest light in existence. For this, they would win the Nobel Prize. Today, we see this light as a nearly uniform glow bathing the entire cosmos, cooled by expansion to just 2.7 degrees above absolute zero. But calling it a baby picture is not just a cute metaphor. It is a literal snapshot of the universe at the tender age of 380,000 years. The near perfection of its temperature, its incredible uniformity, tells us the infant cosmos was remarkably smooth. Yet, when we examine it with incredibly sensitive instruments like the Planck satellite, we find it is not perfectly smooth. Embedded within that uniform glow are tiny variations, minute differences in temperature of just 1 part in 100,000. These are the anisotropies. Think of them as the faint brushstrokes on the canvas of the early universe. These tiny ripples are the gravitational seeds planted during inflation, the slightly denser patches that would, over eons, pull in more matter through gravity. They are the cosmic blueprint, the direct precursors to every galaxy cluster, every filament of the cosmic web, and every vast void we see today. By mapping these subtle patterns with exquisite precision, cosmologists have confirmed the predictions of the Big Bang model with overwhelming evidence. The cosmic microwave background is our most direct line of sight to the universe's infancy, a fossilized echo of the moment it first saw the light. Those faint brushstrokes on the cosmic canvas are the universe's original fingerprints. They are called anisotropies, tiny ripples in the temperature of the cosmic microwave background, and they tell a story that bridges two seemingly separate worlds. On one hand, they are the grand gravitational seeds for all cosmic structure. On the other, they are the magnified ghosts of quantum jitters, whispers from a realm a trillion times smaller than an atom. So, what exactly are these ripples? Think back to the inflationary epoch, that moment of hyper-fast expansion. According to quantum mechanics, empty space is never truly still. It is a seething foam of potential where pairs of particles and their opposites constantly flicker into and out of existence. These are quantum fluctuations, temporary bubbles of something borrowed from nothing. During inflation, the universe expanded so rapidly that these microscopic bubbles did not have time to vanish. Instead, they were stretched, frozen, and imprinted directly onto the fabric of spacetime itself. A region of space that was slightly more dense due to a quantum fluctuation was stretched to the size of a galaxy cluster. A region that was slightly less dense was stretched into a future cosmic void. Inflation took the quantum noise of the ultra-small and blew it up to the scale of the entire cosmos. These stretched fluctuations became the anisotropies we see in the cosmic microwave background. They are the slight overdensities and underdensities in that ancient plasma, differences of just about 1 part in 100,000. That may seem insignificant, but gravity is a patient and relentless force. After the universe became transparent, gravity went to work on those seeds. A region with just a tiny bit more mass had a slightly stronger gravitational pull. Over millions of years, it attracted more and more of the surrounding dark matter and gas. That initial speck of extra density grew, snowballing into a vast cloud, which then collapsed to form the first stars and galaxies. The slightly less dense regions, meanwhile, emptied out, becoming the great voids we see between the galactic filaments. This process, known as gravitational instability, is how the nearly smooth infant universe evolved into the intricate cosmic web of galaxies and clusters we observe today. Every galaxy, every cluster, every filament in the vast architecture of the cosmos can trace its lineage back to a specific quantum ripple in the first trillionth of a second. It is a profound connection. The same rules that govern the behavior of subatomic particles, the rules of chance and probability at the quantum scale, ultimately dictated where galaxies would bloom and where vast emptiness would reign. The universe's largest structures are, in their origin story, quantum mechanical. Yet those quantum seeds could not have built the cosmos alone. They needed an invisible architect, a form of matter that does not shine, reflect, or absorb light. This is dark matter, the universe's most pervasive and mysterious ingredient. Its existence was first hinted at not by what we saw, but by what we saw moving too fast. In the 1930s, astronomer Fritz Zwicky was studying a cluster of galaxies and noticed something bizarre. The individual galaxies were orbiting the cluster's center at such tremendous speeds that, according to the visible mass of stars and gas, they should have flown apart long ago. The cluster was held together by a gravity far stronger than the light could account for. Zwicky called this missing mass Dunkel Materie, dark matter. The evidence became undeniable decades later with galaxy rotation curves. When we look at a spiral galaxy like our own Milky Way, we expect stars on the outer edges, farther from the galactic center, to orbit more slowly, just as Pluto orbits the Sun more slowly than Earth. Observations showed the opposite. Stars at the edge orbit just as fast as those near the center. The only explanation is that each galaxy is embedded within a vast spherical halo of invisible matter, exerting a gravitational pull far beyond the visible disk of stars. This dark matter halo holds the galaxy together. Another line of proof comes from gravitational lensing, a dramatic effect predicted by Einstein. Massive objects warp the fabric of spacetime, bending the path of light from distant galaxies behind them. By measuring how much the light is bent, we can weigh the foreground object. When we look at massive galaxy clusters, the bending is far too severe for the visible matter we see. The true mass, and thus the true gravity, comes from an enormous, diffuse cloud of dark matter enveloping the entire cluster. So what is this stuff? We know it is not made of atoms, the protons, neutrons, and electrons that constitute everything we see and touch. It does not interact with light or the electromagnetic force at all. It feels gravity, and it may also feel the weak nuclear force, but otherwise it passes through normal matter and itself like a ghost. This bizarre nature is precisely what made it the universe's master builder. In the early cosmos, after the cosmic microwave background was released, normal matter was under intense pressure. Ordinary atoms bathed in radiation were pushed apart, unable to clump together easily. Dark matter, being immune to light's pressure, felt only gravity. It began collapsing first, pooling into vast webs and halos under its own weight. These dark matter structures became the gravitational scaffolding for the entire universe. Only later, as the universe expanded and cooled, could normal gas fall into these pre-existing dark matter wells. There it could condense, cool further, and eventually ignite into the first stars and galaxies. Without dark matter's head start providing deep gravitational pits to collect the gas, galaxy formation would have been delayed by billions of years, and the cosmos might be a much emptier, darker place. The hunt to identify dark matter is one of physics' greatest quests. Leading candidates include WIMP, or weakly interacting massive particles. These are theoretical heavy particles that could have been forged in the hot early universe, left over as a cosmic relic. Another intriguing possibility is the action, an extremely light particle born from theories attempting to solve a different deep puzzle in quantum physics. Experiments deep underground and in space are searching for the faintest whisper of these ghostly particles interacting with normal matter. For now, dark matter remains a silhouette defined by the profound and undeniable shadow it casts across the cosmos. Dark matter sculpted the cosmos, but another, stranger force now controls its destiny. This is dark energy, and its discovery turned our understanding of the universe inside out. For decades, cosmologists believed the expansion of the universe, set in motion by the Big Bang, should be slowing down. The gravitational pull of all the matter, both visible and dark, should act as a cosmic brake, gradually decelerating the great outward rush. The only question was whether there was enough matter to one day reverse the expansion, leading to a big crunch, or if it would simply coast forever, slowing to a near halt. Then, in 1998, two independent teams of astronomers made a shocking announcement. By observing distant supernovae, which act as cosmic mile markers, they found the expansion was not slowing at all. It was speeding up. The universe, against all expectation, was accelerating. It was as if you threw a ball into the air, and instead of falling back down, it shot away faster and faster into the sky. This discovery required a radical explanation, a repulsive force powerful enough to overcome gravity on the largest scales. That force is what we call dark energy. While dark matter is an invisible substance that clumps and pulls, dark energy appears to be a property of empty space itself. the more space there is, the more dark energy there is, and thus the stronger its repulsive push becomes. This concept is not entirely new. Albert Einstein, in his theory of general relativity, included a mathematical term he called the cosmological constant. He originally added it to his equations to allow for a static, unchanging universe, which was the prevailing belief at the time. When Edwin Hubble later proved the universe was expanding, Einstein famously called the cosmological constant his greatest blunder. Yet, in a stunning twist of fate, modern observations suggest Einstein may have been right for the wrong reason. His cosmological constant is the leading candidate for what dark energy could be, a constant energy density inherent to the vacuum of space. Its implications are profound. Dark energy now dominates the energy budget of the cosmos, making up about 68% of everything. It has been shaping the universe's large-scale structure for billions of years. In the early universe, matter was denser and gravity's pull was stronger, holding the cosmic expansion in check and allowing galaxies to form. But as the universe expanded and matter thinned out, dark energy's constant push began to win. We now live in an era where this mysterious energy is the dominant force, driving galaxies apart from each other at an ever-increasing rate. This leads to a chilling vision of the far future. If dark energy continues unchecked, it points toward a cold, lonely end known as the Big Freeze. Over trillions of years, galaxies outside our local group will accelerate away, disappearing over a cosmic horizon. Eventually, even star formation will cease, and the universe will become a vast, dark, and ever more empty expanse. The discovery of dark energy reminds us that the cosmos is not just a relic of a violent past, but a dynamic, evolving entity with a future written by forces we are only beginning to comprehend. The universe's first 3 minutes were a cosmic forge of unimaginable power, creating the very first atomic nuclei from the primordial fire. This brief, explosive chapter is called Big Bang nucleosynthesis. For a fleeting window from about 1 second to just 3 minutes after the beginning, the entire cosmos was hot and dense enough to act as a nuclear fusion reactor. The key players were protons and neutrons, which had formed from even more fundamental particles called quarks as the universe cooled. In that searing plasma, these particles slammed into each other with tremendous energy. Initially, single protons and neutrons fused to form deuterium, a heavy isotope of hydrogen. This was a fragile step, as the intense radiation field could easily blast these new deuterium nuclei apart. But as expansion continued to cool the universe, the balance tipped. Once deuterium could survive, a rapid chain reaction began. Deuterium nuclei quickly captured more protons and neutrons, forming helium-3, helium-4, and a minuscule amount of lithium-7. This process was a frantic race against the clock. After about 3 minutes, the universe had expanded and cooled so much that the density and temperature fell below the threshold needed for fusion. The nuclear reaction simply stopped, freezing the elemental abundances in place. The result was a primordial soup of astonishing simplicity. By mass, it was roughly 75% hydrogen nuclei, which are single protons, and 25% helium-4 nuclei, with only trace amounts, less than 1 part in a billion, of deuterium, helium-3, and lithium. This is the foundational chemistry of the cosmos. Every star, every planet, every molecule in your body is built from atoms that began in one of 2 places: this 3-minute furnace of the Big Bang, or the fiery hearts of stars that came billions of years later. Big Bang nucleosynthesis gave us the hydrogen that fuels stars, the helium that fills balloons, and nothing else. The incredible predictive power of this theory is a cornerstone of modern cosmology. When we calculate the expected amounts of these light elements based on the known expansion rate and density of the early universe, the numbers match what we observe in the oldest, most pristine corners of space with stunning precision. This agreement is a powerful confirmation of the Big Bang model itself. It tells us that our understanding of physics, extrapolated back to those first frantic minutes, is fundamentally correct. So the next time you look at the night sky, remember that the simplest, most abundant stuff in the universe, the hydrogen in distant nebulae and the helium in the sun, is a direct relic of creation's first act, a 3-minute burst of fusion that set the stage for everything to come. The smooth glow of the cosmic microwave background was a lie, but a beautiful and necessary one. That near-perfect uniformity held the secret seeds for all the structure we see. The journey from that smooth soup to our lumpy, intricate cosmos is a story of gravity's patient, relentless work over hundreds of millions of years. It begins with those tiny anisotropies, regions where the density was just a fraction of a percent higher than average. In a universe dominated by dark matter, these slight overdensities had a crucial advantage. Dark matter, immune to the pressure of light, felt only gravity's pull. So while ordinary atomic matter was still buffeted by radiation, these dark matter seeds began to quietly collapse. They drew in more dark matter from their surroundings, growing steadily heavier and creating deep gravitational wells in the fabric of space. These were the first dark matter halos, invisible scaffolds that would define the architecture of the future universe. For a long time, that was all there was, an unseen skeleton growing in the dark. This epoch is called the Cosmic Dark Ages, a period after the release of the cosmic microwave background but before the first stars switched on. The universe was a vast, expanding sea of neutral hydrogen and helium gas, threaded with an ever-growing web of dark matter. It was a profoundly silent and dark place. Then, as the halos reached a critical mass, everything changed. Ordinary gas, finally free from the intense radiation pressure of the early cosmos, began to feel the pull of those deep dark matter wells. Vast rivers of hydrogen and helium, hundreds of thousands of light years across, flowed along the filaments of the dark matter web, converging at the intersections where the halos were largest. When these massive clouds of gas crashed into the halos, they did not settle quietly. They swirled with tremendous energy, heating up through the violence of the collision. But to form stars, the gas needed to cool. It did so by radiating away its heat, a slow process that took tens of millions of years. As it cooled, the giant cloud could condense, fragmenting into smaller, denser clumps. Within these densest knots, gravity finally achieved its ultimate triumph. A clump of gas would become so dense and hot at its core that the pressure and temperature ignited nuclear fusion. In a flash that pierced the universal darkness, the first star was born. This was not a star like our Sun. These first stars, often called population 3 stars, were behemoths, likely hundreds of times more massive. They lived fast and died young, burning through their fuel in only a few million years before exploding as spectacular supernovae. These explosions were universe-altering events. They did two vital things. First, they flooded their surroundings with the first heavy elements like carbon, oxygen, and iron forged in their cores. Second, their shockwaves compressed nearby gas, triggering the collapse and formation of the next generation of stars. Around these brilliant, short-lived pioneers, more gas continued to fall into the dark matter halo, spinning and flattening into a disk. The first proto-galaxies were being assembled, glowing islands of light in an ocean of darkness. The cosmic dark ages were over, and a new era of cosmic dawn had begun, illuminated by the fierce light of the first stars. Their explosive deaths were a necessary catastrophe for the cosmos we know. The first stars, known to astronomers as population 3, were unlike anything that shines today. They were titans born from a universe of pure simplicity, composed only of hydrogen and helium, the primordial elements forged in the Big Bang's first 3 minutes. This pristine chemistry made them fundamentally different. With no heavier elements to help cool the giant gas clouds that formed them, these clouds could not fragment into many small stars. Instead, they collapsed into monstrous singularities of light, each potentially hundreds of times more massive than our Sun. Imagine a star so vast its surface temperature could exceed 100,000 degrees, burning with a ferocious blue-white intensity. Their lives were spectacularly brief. A star's lifetime is a race between its nuclear fuel and its own gravity. The more massive the star, the fiercer the fusion in its core, and the faster it burns through its fuel. While our Sun will shine steadily for 10 billion years, these first giants lived for only a few million, a cosmic blink of an eye. Their brilliance, however, was universe-altering. Their intense ultraviolet radiation began to tear apart the neutral hydrogen atoms that filled the cosmos, a process called reionization. For hundreds of millions of years, the universe had been dark and opaque to this kind of high-energy light. Now, these stellar beacons began to punch ionized bubbles into the fog, slowly clearing the cosmic medium and making the universe transparent to ultraviolet light for the first time since the cosmic microwave background was released. But their final act was even more transformative. When such a massive star exhausts its fuel, its core collapses in a heartbeat. The rebound from this collapse triggers a supernova explosion of unimaginable power, outshining an entire galaxy. In that cataclysm, the extreme temperatures and pressures forged atoms heavier than helium for the very first time. Carbon, oxygen, silicon, iron, all the essential ingredients for planets and life, were cooked in those stellar furnaces and then blasted into the void. This was the first pollution of the pristine cosmos, and it was a gift. These heavy elements, scattered by the supernova shockwaves, mixed with the surrounding clouds of hydrogen and helium. When the next generation of stars formed from this enriched material, everything changed. The presence of even trace amounts of elements like carbon and oxygen allowed the gas to cool much more efficiently, enabling it to fragment into smaller, more stable clumps. This is why later generations of stars, like our Sun, are smaller and longer-lived. The violent deaths of the first stars literally changed the rules of star formation, seeding the cosmos with the chemical diversity necessary for rocky planets and ultimately us. We are, in the most literal sense, stardust forged in the hearts and explosive deaths of those first fleeting giants. From the ashes of those first stars rose the first cities of light, the galaxies. Their formation was not a gentle gathering, but a story of epic collisions and mergers, a cosmic construction project that continues to this day. This is the hierarchical model of galaxy formation, and it begins with the dark matter scaffolding we discussed earlier. Small clumps of dark matter holding onto their captured gas formed the first protogalaxies, perhaps only 1/100th the mass of our Milky Way, but gravity is a social force. These small building blocks, drawn together by their mutual attraction, began to crash into one another. Over billions of years, a relentless dance of merger and acquisition built up the majestic spiral and elliptical galaxies we see. The type of galaxy that results depends largely on the violence of its upbringing. Spiral galaxies, like our own Milky Way or the beautiful Andromeda, are the products of relatively orderly mergers. They often form from the steady, gradual accumulation of gas-rich smaller galaxies. When such a merger happens, the incoming gas has angular momentum, a spin. As it settles into the growing dark matter halo, it forms a vast rotating disk. Within this disk, the densest regions collapse to form new stars, creating the iconic spiral arms we see. It is a process of controlled growth, preserving the delicate, spinning structure. Elliptical galaxies tell a different, more brutal story. These are the featureless, football-shaped giants often found at the hearts of dense galaxy clusters. They are the products of major mergers when two large, gas-rich spiral galaxies of roughly equal size collide head-on. In such a catastrophic event, the orderly rotational motion of the disks is completely disrupted. The gas is violently shocked, often triggering a furious burst of new star formation all at once, which quickly exhausts the fuel. What remains is a chaotic swarm of stars orbiting in all directions, settling into a smooth, elliptical shape. You can see this process in action in stunning telescope images, like the antennae galaxies, where two spirals are caught in a slow-motion wreck, their long tidal tails of stars flung out into space. But there is a hidden governor in this process, a monster lurking in the galactic core. At the center of nearly every large galaxy, including our own, sits a supermassive black hole weighing millions or even billions of times the mass of our Sun. During a galactic merger, as gas floods toward the center, it also feeds this black hole. The black hole does not consume quietly. As matter spirals in at nearly the speed of light, it forms a blazing, swirling disk of superheated material, becoming an active galactic nucleus or quasar. This engine can unleash tremendous energy, firing jets of radiation and particles out across the galaxy. This is called black hole feedback. It acts like a cosmic thermostat. The fierce energy from the feasting black hole heats up and blows away the surrounding gas reservoir. With its fuel supply cut off, the black hole quiets down and star formation across the entire galaxy can be suppressed. This feedback process is crucial. It prevents galaxies from growing too large too fast and explains why we do not see galaxies 10 times the size of the Milky Way. The formation of galaxies is not a finished chapter. We see the evidence all around us. Our own Milky Way is currently digesting several small dwarf galaxies, and in about 4 billion years it will merge with the Andromeda galaxy, likely resulting in a new, giant elliptical galaxy. The cosmos is a construction site with galaxies constantly being built, remodeled, and reshaped in a dynamic gravitational ballet. The violent mergers that built galaxies also fed the monsters at their hearts. But this creates a profound timing problem. We see quasars, the blazing beacons powered by supermassive black holes, shining from the universe's infancy when it was less than 1 billion years old. The light from these objects has traveled almost the entire history of the cosmos to reach us. The black holes powering them must have weighed 1 billion times the mass of our Sun or more. How did something so unimaginably massive form so quickly? For a giant black hole to grow, it needs to feast on staggering amounts of gas, but in the early universe, time was the ultimate constraint. There is a speed limit called the Eddington limit, which governs how fast a black hole can swallow matter. If it eats too greedily, the intense radiation from the infalling material actually pushes the surrounding gas away, shutting off the food supply. Even if a black hole ate at this maximum theoretical rate for its entire existence, it would take nearly 1 billion years to grow from a stellar seed to a billion solar mass giant. Yet the universe at that tender age simply had not given it that much time. So how did they cheat? Astronomers are investigating several radical theories. The first skips the seed stage entirely. It is called direct collapse. In the early cosmos, before the first stars polluted space with heavy elements, there could have been vast, pristine clouds of hydrogen gas. Under the right conditions, perhaps in the heart of a massive dark matter halo, such a cloud might have avoided fragmenting into many stars. Instead, the entire cloud, weighing tens of thousands of solar masses, could have collapsed directly into a single massive object. This would not form a star, but a giant black hole seed from the very beginning, a head start of monumental proportions. Another theory involves supermassive stars. The first generation of stars, those population 3 giants, might have occasionally formed with truly extreme masses, over 1,000 times that of our Sun. Such a star would burn furiously and collapse almost immediately, leaving behind a black hole seed hundreds of times more massive than one from a typical supernova. This heavier seed could then grow faster, but perhaps the most dramatic possibility is that the early universe was simply a more efficient feeding ground. The dense, gas-rich conditions shortly after the first galaxies formed might have allowed for episodes of hyper-efficient or super-Eddington accretion. Picture a black hole not sipping neatly from a disk, but gorging itself in a chaotic, messy feast where gas falls in from all directions. In such a frenzy, the radiation might be trapped and unable to escape to push the gas away, allowing the black hole to consume matter at a breakneck pace, far exceeding the normal limit. Finally, there is the power of merger. Smaller black hole seeds formed from the first stars could have rapidly merged together within the crowded centers of young galaxies. Each merger creates a larger black hole, which then has a stronger gravitational pull to draw in even more gas and neighbors. This combination of mergers and rapid feeding could have been a perfect storm for runaway growth. The existence of these ancient quasars is not just a curiosity, it is a direct challenge. It forces us to question our models of how structure emerged in the primordial darkness. Did the first black holes have a different, more massive origin story? Did the rules of physics allow for a more gluttonous era of growth? Solving this puzzle means peering into the dawn of cosmic time, to an epoch where the universe's most destructive forces were also its most brilliant architects. The universe is not a random scattering of lights. Zoom out far enough and you see a pattern of breathtaking order, a vast architecture that connects every galaxy. This is the cosmic web, the largest structure we can possibly conceive. It is a delicate, three-dimensional tapestry woven from threads of galaxies, immense filaments that stretch for hundreds of millions of light years. These filaments intersect at dense nodes where thousands of galaxies swarm together in massive clusters. And between these brilliant threads and knots lie the great voids, unimaginably empty regions of space that can span hundreds of millions of light years across, containing almost no galaxies at all. This is the true skeleton of the cosmos, a structure that mirrors the neural networks of a brain or the frothy bubbles in a sink of soapy water. It is the ultimate expression of gravity's work over billions of years, building up from those tiny seeds in the cosmic microwave background. But how do we see something so immense we are inside it? We map it one galaxy at a time. Projects like the Sloan Digital Sky Survey have undertaken this monumental task. Using a dedicated telescope, it has methodically recorded the positions and distances of millions of galaxies. Distance is the key. It transforms a flat, confusing picture of the sky into a true three-dimensional map. Each galaxy becomes a single point of light in a colossal cosmic cartography project. When you plot those millions of points, the pattern emerges from the noise. You see the filaments, you trace the walls, you identify the vast, dark voids. It is a census of the universe on the grandest scale. This map is a powerful confirmation of our entire cosmic story. The distribution of galaxies in the web matches with stunning precision. The predictions made from the tiny temperature ripples in the cosmic microwave background. Those ancient quantum fluctuations dictated exactly where the dark matter would pool and where the galaxies would eventually follow. Furthermore, the web's very existence and shape are impossible to explain with the gravity of visible matter alone. The sheer scale and connectivity of the filaments require the invisible scaffolding of dark matter to hold them together. The cosmic web is therefore a double proof. It validates the initial conditions of the Big Bang and provides overwhelming evidence for the dark matter that shapes it. We are not just mapping galaxies, we are tracing the ghostly outline of the universe's hidden mass, revealing the grand design written into the fabric of space at the very beginning. Embedded within that vast cosmic web is a ghostly echo, a fossilized sound wave from the universe's fiery infancy. This is baryon acoustic oscillation, a subtle but incredibly precise pattern imprinted on the distribution of galaxies themselves. To understand it, we must travel back again to those first few 100,000 years, when the universe was a dense, hot plasma of light and matter. In that searing soup, gravity was constantly trying to pull regions of slightly higher density together. But there was a counterforce. The intense pressure from the trapped radiation, the photons, pushed back, creating a powerful outward pressure wave. This tug-of-war between gravity's inward pull and radiation's outward push set the entire plasma ringing like a bell. spherical sound waves or acoustic oscillations rippled outward from every overdense seed at nearly 2/3 the speed of light. These waves traveled for nearly 400,000 years until the moment of recombination, when atoms formed and the universe became transparent. At that precise instant, the music stopped. The photons, now free to fly as the cosmic microwave background, carried a snapshot of those frozen wavefronts. But the matter, the baryons, which are the protons and neutrons that make up ordinary atoms, was left behind at the crest of those waves. This created a subtle preference in the universe's structure. Galaxies were more likely to form at two specific distances from any initial seed, right at the original seed's location, and at the distance the sound wave had traveled before it froze. That distance became a cosmic yardstick, a standard ruler etched into the fabric of the cosmos. After billions of years of expansion, that frozen sound wave has been stretched to an immense scale, about 500 million light-years across. Today, when we map millions of galaxies in 3 dimensions, we don't just see a random web. We can detect this subtle statistical preference. If you pick any galaxy in the universe, you will find a slightly higher number of other galaxies separated from it by roughly 500 million light-years. It is as if every galaxy sits at the center of a faint, gigantic bubble, with other galaxies preferentially lining the shell. This is the baryon acoustic oscillation signal, the fossilized imprint of those primordial sound waves. Its power as a tool is breathtaking, because we know the original physical size of this standard ruler from the physics of the early universe. We can use it to measure cosmic distances with phenomenal accuracy. Imagine you have a ruler of known length, say 1 foot. If you hold it close to your face, it appears large. If you hold it far away, it appears small. By measuring how big that 500 million light-year ruler appears to us at different distances, which means looking back to different eras in cosmic history, we can precisely track how the universe has stretched over time. This gives us a direct measurement of the expansion history of the cosmos. It allows us to see exactly when the expansion transitioned from slowing down due to gravity's pull to speeding up under the influence of dark energy. By comparing the apparent size of these acoustic scales at various redshifts, astronomers can constrain the properties of dark energy itself, measuring its strength and whether it has changed over billions of years. It is a gentle, persistent echo from the universe's first moments, now serving as one of our most reliable guides to understanding its ultimate fate. That faint echo from the cosmic dawn helps answer one of humanity's oldest and most vertigo-inducing questions. Is our universe finite, or does it stretch on forever? The answer lies not in a distant edge, but in the overall geometry of space itself, a shape dictated by the total amount of matter and energy it contains. General relativity gives us 3 possible cosmic shapes, each with a different fate. The first is a closed universe shaped like a 4-dimensional sphere. In this geometry, space has positive curvature. If you could travel in a perfectly straight line for long enough, you would eventually loop back to your starting point, just as a ship sailing across the ocean returns to its port. A closed universe contains enough matter and energy that its gravity will eventually overcome expansion, leading to a big crunch. The second is an open universe with a hyperbolic, saddle-like shape of negative curvature. Here, parallel lines would diverge forever. This universe has too little density to ever halt its expansion, destined to expand and cool eternally. The third possibility is a flat universe with 0 overall curvature. Parallel lines stay parallel, and the angles of a triangle add up to exactly 180 degrees. This is the critical balance point, the precise density needed to just barely halt expansion after an infinite amount of time, though dark energy has rewritten that fate. So, which shape is ours? The evidence points overwhelmingly to flatness. The cosmic microwave background provides the clearest test. Think of the patterns in that ancient light as shapes drawn on the fabric of space. If the universe were positively curved like a sphere, those patterns would appear magnified. If it were negatively curved like a saddle, they would appear shrunken. The patterns we observe in the CMB match the predictions for a perfectly flat geometry with astonishing precision. The baryon acoustic oscillations, that fossilized sound wave, provide a second, independent measurement. The apparent size of that standard ruler across cosmic history also confirms a flat universe. This geometric fact has a staggering implication. A flat universe can, in theory, be infinite. There is no requirement for it to wrap around on itself. If space is flat and simply connected, then it has no boundary and extends without end. The part we can see, the observable universe, is just a finite bubble within an infinite whole. Beyond our cosmic horizon, the same rules of physics, the same galaxies and stars, could simply repeat forever. This idea is both exhilarating and deeply unsettling. An infinite cosmos means there could be an infinite number of galaxies, stars, and planets. It resurrects the possibility that somewhere in the vastness beyond our view, there could be an exact copy of you, reading an exact copy of this script in a universe that has no end. Physically, it means the total mass and energy of the cosmos is also infinite, a concept that challenges our intuition at every level, yet we must be cautious. Our measurements show the universe is extraordinarily flat, but they cannot prove it is perfectly flat or simply connected. It could be flat and finite, like a four-dimensional torus, a shape that connects to itself without curvature. For now, the data guides us toward a simple, profound, and humbling conclusion. We live in a universe with no center, no edge, and likely no end. The shape of space sets the stage, but the fate of the cosmos will be written by the mysterious character of dark energy. We have already glimpsed the leading contender, a future called the Big Freeze or heat death. In this scenario, dark energy remains a constant force, as Einstein's cosmological constant suggests. The acceleration of expansion continues unabated. Over trillions of years, all galaxies outside our own local group will be pushed beyond our cosmic horizon, their light redshifted into oblivion. The universe beyond our window will go dark. Within our own merged galaxy, star formation will eventually exhaust the gas supply. The last stars will flicker out, leaving behind a cold graveyard of black holes, neutron stars, and frozen, dead planets. Given enough time, even these remnants may decay through theoretical processes like proton decay. The universe approaches a state of maximum entropy, a uniform, icy sea of diluted particles and radiation at a temperature infinitesimally above absolute zero. It is a quiet, drawn-out end, but dark energy might not be so gentle. What if it is not constant but grows stronger over time? This possibility leads to a far more dramatic and violent finale, the Big Rip. In this model, the repulsive force of dark energy increases until it overwhelms every force that holds things together. First, galaxy clusters would be torn apart. Then, individual galaxies. As the force intensifies, stars are ripped from their orbits. In the final moments, planets are shredded from their stars. Ultimately, in the last fraction of a second, the very atoms that make up all matter are torn asunder, as the nuclear forces that bind nuclei together are overcome. Finally, spacetime itself is ripped apart at the most fundamental level. The universe ends not with a whimper, but with a catastrophic, instantaneous disintegration of reality. This fate hinges on a specific and currently unproven property of dark energy called the phantom energy model. While terrifying, it is not the leading prediction. There remains a nostalgic, though increasingly unlikely, alternative, the Big Crunch. This was the classic ending before dark energy's discovery. It requires that the density of matter in the universe is high enough and dark energy weak enough for gravity to eventually reverse the expansion. Galaxies would begin rushing together, space would contract, and the temperature would rise. The cosmic microwave background would heat up from its faint glow to a blazing fire. Galaxies would merge and stars would be destroyed as the universe collapses back toward an ultra-hot, ultra-dense state, a mirror image of the Big Bang. Some theories even suggest this could lead to a cyclical universe, a big bounce where the crunch births a new expansion in an endless cycle. However, our measurements of a flat, accelerating universe make the Big Crunch the least probable of the three. These are not just speculative stories, they are mathematical extrapolations of the clues we have today. The ultimate fate is encoded in the unknown nature of dark energy. Is it truly constant, or does it evolve? By measuring the expansion history with even greater precision, using tools like baryon acoustic oscillations and distant supernova, we are essentially reading the final chapter of the universe's formation story, written in invisible ink at the very beginning. The force that now drives galaxies apart will one day decide how the grand cosmic narrative ends. Our universe may be just one page in an infinite cosmic library. This is the multiverse hypothesis, a breathtaking idea that emerges naturally from the leading theories of our cosmos's earliest moments. Remember eternal inflation, the concept that our universe underwent a brief, hyper-fast expansion. Some versions of this theory suggest that inflation never truly ends everywhere. Instead, it stops in localized patches like bubbles forming in a pot of boiling water. Each of these bubbles becomes its own separate universe, with its own Big Bang and its own subsequent history, forever disconnected from our own. Meanwhile, the inflationary space between these bubbles continues to expand eternally, spawning an endless number of new bubble universes. This is the inflationary multiverse. String theory, a candidate for a theory of everything, adds another layer. It suggests there could be an astronomical number of possible ways for the extra dimensions it proposes to be compactified or folded up. Each different configuration could result in a universe with a completely different set of fundamental forces and particles. In this string theory landscape, each stable configuration represents a possible universe with its own unique physics. So, what would these other universes be like? The possibilities are staggering. In one bubble, the strength of gravity might be 1,000 times stronger, causing stars to burn out in a flash. In another, the nuclear forces might be too weak to bind protons and neutrons, so atoms never form. The cosmological constant, our dark energy, could be vastly different, causing a universe to collapse instantly or fly apart before the first star ignites. The fundamental constants that make our universe tick, the fine structure constant, the mass of the electron, the strength of gravity, are not written in stone by any law we know. They appear to be arbitrary numbers, and in a multiverse, they would take on different values in different bubbles. This leads to a profound and controversial question. Why does our universe have just the right constants to allow for galaxies, stars, planets, and life? If the strength of the strong nuclear force were just a few % different, carbon, the backbone of life, might never form in stars. If dark energy were slightly stronger, the universe would have blown apart before any structure could form. The multiverse offers a potential answer, the anthropic principle. In its simplest form, it states that we can only observe a universe that is capable of producing observers. In an infinite or near-infinite multiverse where every possible set of physical laws exists, it is no surprise that we find ourselves in one of the rare, fine-tuned bubbles where life is possible. We are not here because of a miraculous cosmic coincidence, but because we could not be anywhere else. It is a cosmic version of the observation that a fish lives in water because it could not survive on land. This idea is as fascinating as it is untestable. By definition, these other universes are causally disconnected from our own, existing beyond any possible horizon we could ever observe. This places the multiverse at the very edge of science, a logical extension of our best theories that currently resists direct verification. Yet, it compels us to think deeply about the nature of reality. Are the laws of physics necessary and universal, or are they merely local bylaws in our particular cosmic neighborhood? The multiverse suggests that all possible realities might exist somewhere, making our own existence both profoundly special and, in an infinite sea of possibilities, utterly ordinary. The cosmic microwave background should be the ultimate symbol of cosmic democracy, a perfectly uniform glow with no preferred direction. Yet, some of its largest patterns whisper of a strange cosmic conspiracy, a hint of directionality that has earned the ominous nickname, the axis of evil. This is not a malevolent force, but a statistical anomaly so unsettling it challenges a core assumption of cosmology, isotropy. Isotropy means the universe looks the same in every direction, a fundamental pillar of the Big Bang model. The CMB is remarkably isotropic, but when scientists subtract the overall uniform glow to study the tiny temperature fluctuations, they find something peculiar. On the very largest scales, patterns of warmer and cooler spots appear to have a subtle alignment, not with some distant cosmic landmark, but eerily with the plane of our own solar system. One axis of this alignment even seems to point toward the constellation Virgo. This is deeply strange. It is as if the universe's oldest light holds a faint imprint of our local neighborhood, a connection that should be cosmically impossible. The solar system is an insignificant speck formed 9 billion years after the CMB was released. For its orientation to be somehow linked to the entire universe's structure would be like finding your hometown street map drawn into the bedrock of a continent. So what could explain this? The most likely and least exciting answer is that it is a statistical fluke. We have only one universe to observe, and when you analyze a vast amount of data, you can sometimes find patterns that look significant purely by chance. It could also be an artifact of how we process the data from spacecraft like WMAP and Planck, subtle errors in calibration, or the way we subtract the foreground glow of our own Milky Way galaxy might inadvertently leave behind a false signal that just happens to align with our solar system. Scientists have rigorously checked for these systematic errors, and while some potential sources have been identified, the anomaly stubbornly persists at a low level of significance. This leads to the truly tantalizing possibility that the axis of evil is a real clue. If it is not a fluke or a mistake, it could mean our universe is not perfectly isotropic on the largest scales. Perhaps there is a pre-existing structure, a vast cosmic texture, or a preferred direction imprinted from a time before the Big Bang that subtly tilted the playing field. Some speculative theories even suggest it could be evidence of our universe colliding with another bubble universe in the multiverse during its inflationary infancy, leaving a bruise on the sky. For now, the axis of evil remains an unsolved mystery, a ghost in the cosmic data. It is a powerful reminder that our most cherished models are always subject to the next surprising observation, and that the universe may still hold profound secrets written in its oldest light. The universe's survival hinged on a tiny, unexplained bias. For every star, planet, and galaxy we see to exist, a fundamental crime had to be committed in the first second of creation. The laws of physics, as we understand them, are remarkably fair. They treat matter and antimatter as perfect mirror images. For every particle of matter, like an electron or a quark, there is an antiparticle with the opposite electric charge. When a particle meets its antiparticle, they annihilate in a flash of pure energy. According to this perfect symmetry, the Big Bang should have created precisely equal amounts of matter and antimatter. All of those particles should have found their antimatter partners and mutually destroyed one another, leaving behind a universe filled with nothing but radiation. No atoms, no stars, no us, and yet here we are. The fact that you are watching this, that anything exists at all, tells us something profound. In that first moment, the symmetry was broken. For every billion antimatter particles, there were 1,000,000,001 matter particles. After the catastrophic annihilation, that 1 in a billion survivor was left over. Every single atom in the cosmos is made from that leftover debris. This is the mystery of baryon asymmetry, and it is one of the most urgent questions in physics. In 1967, the Soviet physicist Andrei Sakharov outlined the three conditions needed for this imbalance to occur. First, the universe must be out of thermal equilibrium, meaning it cannot be in a perfectly stable, uniform state. The rapid expansion and cooling of the Big Bang provided this perfectly. Second, there must be processes that violate the conservation of baryon number. Baryons are particles like protons and neutrons, and their number was thought to be always conserved. Sakharov said this rule had to be broken. Third, and most crucially, there must be a violation of both charge symmetry and parity symmetry, together called CP violation. This means the laws of physics must treat matter and antimatter slightly differently, breaking the perfect mirror. We have actually observed CP violation in the lab. In experiments with particles called kaons and B mesons, scientists have seen that these particles and their antiparticles decay at very slightly different rates. It is a real, measurable crack in the mirror. The problem is, the amount of CP violation we have seen is far, far too small. It is like finding a single grain of sand when you need an entire beach. The known sources are insufficient by many orders of magnitude to explain the overwhelming dominance of matter in our universe. This means the answer must lie somewhere we have not yet looked. The hunt is on for new physics, for new particles or interactions that could have tipped the scales dramatically in those first fractions of a second. Experiments at the Large Hadron Collider are searching for signs of these processes. Others are studying the properties of neutrinos, ghostly particles that may be their own antiparticles which could hold a key. Some theories point to events in the very early universe, like phase transitions during the separation of the fundamental forces, that could have acted like a cosmic filter, preferentially producing more matter. Solving this mystery is not an academic exercise. It is a search for the reason anything exists at all. That 1 in a billion imbalance was not just a lucky break, it was the foundational event that made the cosmos tangible. Without it, the universe would be a silent, empty void with no one to wonder why. That 1 in a billion imbalance gave us a universe, but to understand its very first moment, we must confront a deep and fundamental crack in our understanding of reality. Our two most successful theories of physics are at war. On the grand stage of galaxies and the cosmos, Einstein's general relativity reigns supreme. It describes gravity not as a force, but as the curvature of spacetime itself, a dynamic geometry shaped by mass and energy. It tells us how planets orbit, how light bends, and how the universe expands. Yet, in the realm of the vanishingly small, the world of atoms and particles, a different set of rules takes over. Quantum mechanics governs this domain with breathtaking precision, but its rules are probabilistic, strange, and built on uncertainty. Particles can be in two places at once. They can tunnel through barriers, and they pop in and out of existence from the vacuum. The problem is, these two magnificent theories are utterly incompatible. General relativity is smooth, continuous, and deterministic. Quantum mechanics is grainy, probabilistic, and discontinuous. When we try to apply the equations of general relativity to the tiny, dense conditions of the universe's birth, they break down completely, predicting an impossible point of infinite density, the singularity. This tells us our map is incomplete. To see past that singularity, to truly describe the Planck epoch, we need a theory that marries these two worlds. We need a theory of quantum gravity. This is the holy grail of modern physics, a framework where gravity itself is understood to have quantum properties. Two of the most prominent candidates offer radically different visions. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating strings. Different vibrations of these strings correspond to different particles, like notes on a guitar string. Crucially, one of these vibrational modes gives rise to the graviton, the hypothetical quantum particle that would carry the gravitational force. To make the math work, string theory requires extra dimensions of space, curled up at scales so small we never perceive them. It is an elegant, mathematically rich framework that promises to unify all forces and particles. The other major approach is loop quantum gravity. It takes a more direct route, attempting to quantize spacetime itself. In this view, space is not a smooth continuum, but woven from a fabric of tiny, discrete loops. Think of it as a cosmic mesh with a smallest possible unit of area and volume. This has a profound implication for the Big Bang. If space is granular, it cannot be compressed to an infinitely dense point. Instead, as we rewind time, the density reaches a maximum and then rebounds. This leads to the concept of a quantum bounce. The Big Bang may not have been the absolute beginning, but rather a great rebound from a previous cosmic phase that contracted. Our universe could be one turn in an endless cycle of expansion and contraction with no singular start. These ideas are not just mathematical curiosities. They are our best attempts to answer what happened at time zero. A successful theory of quantum gravity would allow us to peer beyond the veil of the Planck epoch, to understand if the universe truly had a beginning or if it has always existed in some form. It seeks to answer the ultimate question of Genesis not with philosophy, but with the precise language of physics, revealing the quantum architecture of spacetime itself. The search for dark matter's identity leads us to a truly ancient possibility, relics forged not in dying stars, but in the chaos of the cosmos's first second. These are primordial black holes, hypothetical objects that could solve two great mysteries at once. Unlike the black holes we know, which form from the collapsed cores of massive stars, primordial black holes would have been born directly from the extreme pressure and density fluctuations in the infant universe. In that seething, hot soup, regions that were significantly denser than average could have collapsed under their own gravity directly into black holes, bypassing the star stage entirely. They could have formed with almost any mass, from as small as an asteroid to many times the mass of our Sun. This is where the dark matter connection becomes compelling. If vast numbers of these primordial black holes were created, especially in a certain mass range, they could be floating invisibly throughout galactic halos right now, providing the gravitational glue we desperately need. They would be perfect dark matter candidates, massive, invisible, and interacting only through gravity. The idea is elegant, but the universe has a way of testing our elegant ideas. Observational constraints have severely narrowed the window where these objects could make up all of dark matter. If too many small, asteroid-mass primordial black holes existed, their gravitational influence would disrupt the delicate structures of star clusters, an effect we do not see. If they were as common as stars in the mass range of our Sun, they would frequently pass between us and distant stars, causing a noticeable brightening due to gravitational microlensing. Surveys have watched for these events and found far too few to account for all the dark matter. For decades, this left the hypothesis on the fringe. But then, gravitational wave astronomy opened a new door. When the LIGO Observatory detected the first ripples from colliding black holes, it found them to be surprisingly heavy, around 30 times the mass of our Sun. Stellar black holes of that size are difficult to explain with our current models of star death. Could some of these be primordial black holes, survivors from the universe's birth? The possibility has revived serious interest. The hunt is now more sophisticated. Astronomers are using the subtle warping of starlight, not just from single stars but from entire galaxies, to search for the collective shadow of a population of wandering, planet-mass primordial black holes. Future telescopes like the Roman Space Telescope will conduct vast microlensing surveys with unprecedented precision, scanning for the telltale flickers that could betray these ancient ghosts. Finding them would be a revolution. It would mean that dark matter is not an exotic new particle, but a fossil of the universe's most violent infancy, and that the cosmos is threaded with invisible remnants of its own explosive birth. The singularity at time zero is a mathematical warning sign, a place where our physics fails. But what if that failure is not a wall, but a door to a stranger truth? Did time itself have a beginning, or is our linear perception of past, present, and future an illusion created by our place within the cosmos? The classical Big Bang model presents a stark answer. At that point of infinite density, the fabric of spacetime itself emerges. There is no before because time is part of the universe's structure. Asking what came before the Big Bang is like asking what is north of the North Pole. The question simply has no meaning within that framework. Yet the human mind, and indeed some of our most advanced theories, rebel against this idea of an absolute beginning from nothing. The quest to resolve the singularity has led to proposals that reshape our understanding of time in its most radical form. One of the most profound is the Hartle-Hawking no-boundary proposal, put forward by physicists James Hartle and Stephen Hawking. In this model, the universe does not have a sharp, singular beginning like the tip of a cone. Instead, think of the origin more like the Earth's South Pole. When you stand at the South Pole, the concept of going further south ceases to exist. All directions lead north. Hartle and Hawking applied a similar idea using the tools of quantum mechanics and imaginary time, a mathematical concept where time behaves like a dimension of space. In this picture, as we wind the cosmic clock back toward the beginning, the familiar dimension of time smoothly transitions or fades into a fourth dimension of space. The universe becomes a closed, four-dimensional surface without any edge or boundary, like the surface of a sphere. There is no point of creation, no moment of infinite density, because there is no boundary where time starts. The universe just is. This is not a universe that pops into existence at a specific time. It is a self-contained whole where the question of a first moment becomes as meaningless as asking for the starting point on the surface of a ball. It exists in a state of quantum superposition, a sum over all possible histories that lead to the cosmos we observe. This idea elegantly banishes the troublesome singularity, but it comes at a profound philosophical cost. It suggests that time, as we experience it, is not fundamental. Our arrow of time, the relentless flow from past to future driven by increasing entropy, may be an emergent property, a large-scale feature that arises from the specific conditions within our universe, much like wetness emerges from the collective behavior of water molecules, though no single molecule is wet. Other cyclical models, like the Big Bounce from loop quantum gravity, offer a different vision. Here, time is eternal. Our expanding universe is simply the latest phase following a previous contraction. There was no beginning, only an endless cycle of expansion and crunch, with time flowing continuously through each transition. Each of these models challenges our deepest intuitions. They ask us to consider that the flow of time may be a local phenomenon, not a cosmic rule. The search for the beginning of time is ultimately a search for the boundary of our understanding. Whether time emerged, transitioned, or has always been, the answer lies in that first fleeting instant where our theories of the very large and the very small must finally meet, rewriting not just the story of the cosmos, but the very nature of reality itself. The final stars will not die with a bang, but with a slow, cold sigh that echoes for eons. Long after the last red dwarf has flickered out, trillions of years from now, the cosmos will enter its final degenerate era. The only sources of light will be the cooling embers of stellar corpses, white dwarfs and neutron stars, radiating their leftover heat into an ever colder void. A white dwarf, the Earth-sized core of a star like our Sun, begins this phase glowing white-hot, but with no fusion to sustain it, it can only cool. Over tens of trillions of years, it will fade from white to yellow to red and finally to black, becoming a cold, crystalline mass of carbon and oxygen, a black dwarf. These dark orbs will be the final monuments to the age of stars, drifting silently through the expanding darkness. Meanwhile, the universe's most enigmatic objects, black holes, face their own slow dissolution. According to Stephen Hawking's theory, black holes are not perfectly black. Due to quantum effects at their event horizons, they can slowly leak radiation, losing mass over time. This Hawking radiation is a whisper of particles escaping the black hole's grip. For a stellar mass black hole, this process is unimaginably slow, taking longer than the current age of the universe to become significant. But given enough time, on scales of 10 to the power of 100 years, even the supermassive black holes at galactic centers will evaporate in a final, faint burst of particles. The universe by then will be unrecognizable. Dark energy will have driven all remaining galaxy clusters beyond each other's cosmic horizons, leaving every stellar remnant in profound isolation. Space will be vast, cold, and nearly empty, a sea of expanding darkness punctuated only by these rare, cold cinders and the fading echo of evaporated black holes. It is a poetic and haunting conclusion to the epic narrative of formation, a quiet fade to black written by the same physics that once ignited the first brilliant dawn. But even the most careful measurements of this cosmic fate are now pointing in conflicting directions, revealing a crack in our otherwise coherent story. This is the Hubble tension, a stubborn and growing discrepancy that has cosmologists both puzzled and excited. The problem is deceptively simple. We have two primary ways to measure how fast the universe is expanding right now, a number called the Hubble constant. The first method looks back to the infant universe, using the cosmic microwave background as our guide. By analyzing the precise patterns in that ancient light, we can calculate how fast the universe was expanding then, and then use our model of cosmic evolution to predict what the expansion rate should be today. This is like calculating how fast a car should be going now based on a detailed photograph of its engine and acceleration from a minute after it started. The second method measures the expansion directly in our local, modern universe. We use celestial mile markers like Cepheid variable stars and Type Ia supernova, whose intrinsic brightness we know. By measuring how bright they appear from Earth and how much their light has been stretched or redshifted, we can directly calculate the current expansion rate. This is like using a radar gun to measure the car's speed right now. Both methods are incredibly sophisticated, backed by Nobel Prize-winning science. The tension is that they disagree. The early universe measurement from the Planck satellite gives a slower, more stately expansion rate. The local measurement from projects like the Hubble Space Telescope and the SH0 team gives a faster, more urgent rate. The difference is not large, only about 10%, but it is far greater than the estimated errors in either measurement. This is not a minor rounding error. It is a persistent, glaring mismatch that has survived over a decade of increasingly precise observations. It matters because it suggests a fundamental flaw in our otherwise beautiful and successful model of the cosmos, the lambda-CDM model. If our measurements are correct, then something is missing from the story. Perhaps there are subtle, unknown systematic errors in one of the methods, a miscalibration of the cosmic distance ladder we have not yet found. The more thrilling possibility is that we are seeing the fingerprints of new physics. Maybe dark energy is not a constant but has been changing strength over cosmic history, subtly altering the expansion rate in a way our models do not account for. Or perhaps there is an unknown type of neutrino or a feature in the early universe's physics that modifies our interpretation of the cosmic microwave background. The Hubble tension is not just a technical dispute, it is a potential crisis in cosmology. It is a signal that our map of the universe from its first second to its present day may have a crucial piece out of place. Resolving it could mean discovering a new ingredient in the cosmic recipe or rewriting a chapter in the story of dark energy, forcing us to see the universe's expansion in a completely new light. The Hubble tension is a modern puzzle, but a far more radical idea challenges the very bedrock of our science. Could the laws of physics themselves be changing? We assume the fundamental constants are fixed for all time and space, the unchanging rules of the cosmic game. The fine structure constant governs the strength of electromagnetism, dictating how atoms hold together. The mass of the electron sets the scale of chemistry. If these numbers were even slightly different, stars would not burn, molecules would not form, and life as we know it would be impossible. Their precise values seem like a miraculous coincidence, fine-tuned for our existence. But what if they are not permanent fixtures? What if they were set in the early universe and have been slowly drifting ever since? This is not science fiction, it is a serious line of scientific inquiry, and astronomers have gone looking for evidence by turning the universe into a time machine. They study the light from quasars, the brilliant cores of ancient galaxies billions of light years away. As this light travels to us, it passes through vast clouds of intergalactic gas. Atoms in these clouds absorb specific wavelengths of the quasar's light, creating dark lines in its spectrum like a barcode. The positions of these lines depend precisely on the values of the fundamental constants at the time and place the absorption occurred. By comparing these ancient barcodes to the ones we create in labs on Earth today, we can check if the constants have changed. The results are controversial and electrifying. One team, led by astronomer James Webb, analyzed quasar data and reported a tantalizing signal. They found that billions of years ago, in certain directions of the sky, the fine structure constant might have been slightly smaller. The change is minuscule, a few parts in a million, but if real, it would be revolutionary. It would mean the strength of the electromagnetic force was weaker in the past, and perhaps it varies across the cosmos. Other teams have tried to replicate this finding with mixed results, some supporting it, others finding no change at all. The debate is intense because the stakes are cosmic. If the constants are truly inconstant, it would mean our universe is not just evolving in its content, but in its very rulebook. The physics that governs a distant galaxy might be subtly different from our own. This could offer a dramatic solution to the fine-tuning problem. Instead of a single, perfectly tuned universe, we might live in one where the constants naturally evolve toward life, permitting values over time. Our local physics would then be a snapshot, not a decree. A changing fine structure constant would also force us to rewrite our models of stellar nuclear fusion and the early universe's particle physics, with cascading effects on everything from the formation of the first elements to the life cycles of stars. For now, the evidence remains on the knife edge, a whisper in the data that could be a statistical ghost or the first hint of a deeper, more dynamic layer to reality. It asks us to consider that the laws we hold as eternal might be more like local customs, shaped by the unfolding story of the cosmos itself. Those whispers of changing constants are not the only ghosts in the cosmic machine. A trillion of them pass through your body every second, remnants of the universe's first birthday. Neutrinos are the universe's most elusive particles, so shy they were once thought to be massless ghosts. Born in the nuclear inferno of the Big Bang's first second, they hold a secret history even older than the cosmic microwave background. To understand their role, we must go back to that searing, dense beginning. For the first full second after the Big Bang, the universe was so hot and dense that even these phantom particles were trapped. Neutrinos constantly interacted with the thick soup of protons, electrons, and photons, bouncing around and helping to keep everything in a state of hot, scrambled equilibrium. But then, as the cosmos expanded and cooled past about 10 billion degrees, something pivotal happened. The energy of the particle soup dropped below the threshold needed for neutrinos to interact frequently. In a cosmic instant, they decoupled. They stopped bumping into other matter and simply streamed freely across the expanding universe, never to be significantly disturbed again. This happened a mere 1 second after the beginning, nearly 400,000 years before the photons of the cosmic microwave background would be set free. This created a cosmic neutrino background, a sea of these ancient particles flooding all of space. It is, in theory, the oldest fossil in the universe, a snapshot from its very first second of independent existence. But detecting it is a monumental challenge. While the CMB photons were released at an energy equivalent to several thousand degrees and have since cooled to microwave wavelengths, the Big Bang neutrinos have been stretched and cooled by 14 billion years of expansion to an almost unimaginably low energy. They are now theorized to have a temperature of just about 1.9 degrees above absolute zero, even colder than the CMB, and they interact so weakly that they pass through entire planets like they are not even there. Catching one of these specific, primordial neutrinos is like trying to pick out a single, whispered word in a hurricane, yet their influence is written across the cosmos in subtler ways. For decades, neutrinos were assumed to be massless, traveling at the speed of light. Then, experiments revealed they do have a tiny mass, a discovery that won the Nobel Prize. This minuscule heft changes everything for the cosmic story. In the early universe, neutrinos were moving at nearly light speed. This incredible velocity made them hot dark matter. Unlike the cold dark matter that clumps easily to form scaffolding, fast-moving neutrinos streamed smoothly out of the tiny, dense seeds that were trying to grow into galaxies. This streaming effect suppressed the growth of the very smallest structures in the cosmic web. It is a faint, smoothing brushstroke on the canvas of creation. By studying the large-scale distribution of galaxies and the detailed patterns in the cosmic microwave background, cosmologists can actually see the imprint of this suppression. The data tells us that neutrinos, while incredibly light, cannot make up more than a small fraction of dark matter. Their ghostly presence set a minimum scale for the first clumps of matter, subtly shaping the architecture of the universe from the bottom up. Finding the cosmic neutrino background would be the ultimate archaeological dig, a direct probe of the universe at 1 second old. It would let us test our models of particle physics under conditions no lab on Earth could ever recreate. For now, this oldest light remains a theoretical whisper, a sea of ghosts from the first moment of cosmic childhood, holding secrets we are only beginning to learn how to hear. That sea of neutral hydrogen was the universe's longest night, but it did not last. A new dawn was coming, one that would fundamentally change the cosmos from the inside out. This is the epoch of reionization, the great reawakening of light. For hundreds of millions of years after the cosmic microwave background was released, the universe was filled with a fog of neutral hydrogen atoms, each a simple pairing of a proton and an electron. Space was transparent only to certain wavelengths, but to the high-energy ultraviolet light needed to tear atoms apart, it was utterly opaque. Then the first stars and galaxies ignited. These were not like our gentle sun. The earliest stars were colossal, burning with a ferocious blue-white intensity, and their cores produced a torrent of ultraviolet photons. When these energetic particles of light slammed into the surrounding neutral hydrogen, they did something dramatic. They knocked the electrons clean off the protons, ionizing the atoms and turning the calm fog back into a turbulent, charged plasma. This process did not happen evenly or all at once. Think of it like a foggy landscape at sunrise. The first brilliant stars acted like lone streetlights, punching small, isolated bubbles of ionized gas into the darkness. As more stars ignited and the first galaxies assembled, these bubbles grew, overlapped, and eventually merged. Over several 100 million years, this patchwork of light steadily burned away the cosmic fog, making the vast spaces between galaxies transparent to ultraviolet light once again. The universe, for the second time in its history, became see-through. But how can we possibly study an event that happened over 13 billion years ago, an era with no stars to illuminate it directly? Astronomers use cosmic lighthouses, the most brilliant beacons in the universe, quasars. A quasar is the blazing core of a distant galaxy, powered by a voracious supermassive black hole. Its light is so intense it can be seen from the farthest reaches of space and time. We use these quasars as backlights. As their light travels toward us, it passes through the ancient hydrogen fog from the epoch of reionization. Neutral hydrogen is very good at absorbing a very specific wavelength of ultraviolet light. So when we look at a quasar's spectrum, its fingerprint of light, we search for a telltale shadow, a dark band where that specific wavelength has been eaten away by the intervening hydrogen. This band is called the Lyman alpha forest, and it is a direct record of the fog's thickness at different distances and thus different times in the past. By studying many quasars in different directions, we can map how the fog cleared. The data paints a picture of a gradual process beginning around 400 million years after the Big Bang and largely complete by about 1 billion years. But to truly understand reionization, we need to see the actors themselves, the first galaxies that did the work. This is where our newest window on the cosmos comes in, the James Webb Space Telescope. Webb is uniquely designed to see the infrared light from these incredibly distant, ancient galaxies. Their light has been stretched so far by cosmic expansion that it arrives as infrared, invisible to our eyes and to Hubble. With Webb, we are not just seeing the shadow of the fog, we are beginning to see the streetlights that burned it away. We are finding galaxies from that era that are brighter, more numerous, and perhaps more efficient at producing ionizing radiation than many models predicted. Each new faint smudge of light Webb discovers is a piece of the puzzle, helping us understand what kind of objects, stars, or even early black holes had the power to reionize the entire cosmos. This epoch was more than just a clearing of fog. It was the final major transition of the universe, setting the stage for the transparent, structured cosmos we observe today, where light can travel freely for billions of years to tell us its story. Perhaps the universe has no beginning or end, only a series of endless rebirths. This is the heart of a radical theory from Nobel laureate Roger Penrose, known as conformal cyclic cosmology. It proposes a breathtaking vision where the far, far future of one universe becomes the hot, dense Big Bang of the next, in an eternal cycle without a singularity. The key lies in a mathematical transformation, a stretching and rescaling of spacetime itself. In the unimaginably distant future, after the last black hole has evaporated and all matter has decayed into radiation, the universe becomes an almost featureless sea of massless particles like photons and gravitons. In this state, the concept of distance and time loses all meaning because there are no massive objects to define a scale. Penrose argues that this endless, smooth, cold future can be mathematically rescaled or conformally transformed to match the hot, dense, smooth beginning of a new universe. The infinite future becomes the 0 point of a new Big Bang. It is a cosmic phoenix rising from its own ashes in a form we can barely comprehend. This is not a traditional big crunch and bounce, but a more subtle, geometric transition where the universe forgets its scale and starts anew. To support such a monumental claim, one would need evidence written into the sky itself. Penrose believes he has found it. He and his colleagues point to strange, circular patterns of warmer temperature in the cosmic microwave background, which they call Hawking points. These are theorized to be the imprints of supermassive black holes from the previous eon, or cycle of the universe. In the conformal cyclic cosmology model, when a black hole evaporates via Hawking radiation in the final moments of an eon, that burst of energy is conformally mapped onto the next eon's Big Bang, appearing as a circular anomaly in the CMB. These points are named for Stephen Hawking, who predicted black hole evaporation. Finding them would be a direct fossil, a scar from a universe that existed before our own. The scientific response has been intensely skeptical, as it must be for any idea this revolutionary. Many cosmologists argue that the patterns Penrose identifies are consistent with what you would expect from random statistical fluctuations in the CMB data. The human brain is exceptional at finding patterns, even where none exist, a phenomenon called pareidolia. Independent teams analyzing the same Planck satellite data have generally concluded that these alleged Hawking points do not stand out significantly from the noise. The burden of proof for such an extraordinary claim is immense, and the mainstream cosmological community has not been convinced that the evidence meets that burden. Yet the value of conformal cyclic cosmology lies not just in its potential truth, but in its bold challenge to our assumptions. It forces us to ask what truly defines a beginning. If time and distance lose all meaning at the extremes of scale, then the question of what came before our Big Bang might be transformed into a question of what lies in the conformal geometry of eternity. Whether Penrose's specific theory is correct or not, it expands the landscape of possibility, reminding us that our current story of a single, linear universe from a singular beginning might be just one chapter in a much grander and far more mysterious book. Our journey through 30 questions has brought us face to face with the edges of our understanding. We have mapped the cosmos from a quantum whisper to a vast web of galaxies, yet the deepest mysteries remain those we cannot yet see. The true story of the universe's formation is woven from these profound unknowns. Dark matter sculpts every galaxy, but we do not know what it is. Dark energy drives the cosmos apart, but we do not know why it exists. Inflation perfectly explains our universe's smooth, flat geometry, but we do not know what triggered that explosive growth or if it truly happened everywhere. And at the very beginning, the initial singularity remains a veil, a point where our two great theories of reality clash and fall silent. These are not separate puzzles. They are interconnected chapters of a single grand mystery. The nature of dark energy influences how structure formed. The properties of dark matter dictated where the first stars could ignite. The physics of inflation may hold the key to why there is something rather than nothing. Each unanswered question is a thread, and pulling on one tugs at the foundations of all the others. This is not a failure of science, but its greatest promise. The formation of the universe is a story still being written, with every new observation adding a sentence and every stubborn paradox threatening to rewrite a chapter. We stand at a thrilling precipice, new eyes on the cosmos like the James Webb Space Telescope and the upcoming Vera Rubin Observatory are peering back to the very first galaxies and mapping the cosmic web in unprecedented detail. Deep underground, laboratories hunt for the faint tremor of a dark matter particle. In space, missions are designed to measure the expansion history with even finer precision, probing the character of dark energy. And theorists are weaving ever more daring ideas, from quantum gravity to the multiverse, providing a target for these experiments to aim for. The next great discovery may not answer a single question, but could unravel several at once, revealing a universe far stranger and more wonderful than we have yet dared to imagine. Our map is incomplete, and that is the most exciting truth of all. From that single quantum spark to the vast cosmic web we see today, the story of our universe is one of breathtaking transformation. We have traced its epic journey from the unimaginable first instant where all forces were one, through the explosive smoothing of inflation that set the stage for everything. We witnessed the first atomic nuclei forged in the 3-minute furnace of Big Bang nucleosynthesis, creating the hydrogen and helium that would become the fuel for all stars. We saw the universe fall into a deep, dark sleep, only to be awakened by the brilliant, violent first stars whose explosive death seeded the cosmos with the elements of life. We watched gravity patiently sculpt the dark matter scaffolding, drawing in gas to build the majestic galaxies and the immense filaments of the cosmic web. And we confronted the forces that now shape its destiny, the ghostly pull of dark matter and the mysterious push of dark energy. Each answer we find, from the cosmic microwave background to the Hubble tension, does not close a chapter. Instead, it peels back a layer to reveal a deeper, more fundamental mystery waiting beneath. The formation of the universe is not a solved puzzle, but a living inquiry, a story still being written with every new telescope pointed at the sky and every new experiment buried deep underground. So, what is the one cosmic question that fills you with the most wonder? Share your biggest mystery about the universe in the comments below. If you enjoyed this deep dive into the story of everything, be sure to like this video and subscribe for more journeys to the edges of space, time, and understanding. The universe is the greatest story ever told, and the next chapter is waiting to be discovered. Stay curious.